Hi. Let me give you a little bit of stuff on sequences and summation notation. Sequences you probably encountered in first or third grade or something like that, where you just got a number pattern. 1, 4, 9, 16, 25, and you'd answer questions like, what are the next 3 terms in the sequence? You know, oh, maybe you just said, what's the next number in the pattern? And you recognize these are perfect squares, and the next one would be 36, and the next one would be 49, 7 times 7, and then 64, 8 times 8. Okay, we want a more sophisticated definition of what a sequence is now. And I think it's kind of a surprising definition, to tell you the truth. We're going to say a sequence, a sequence of numbers, a number pattern, is a function. Whoa. So remember functions, you got that in 2.1. The definition was it's a relation, an input-output relation, in which every element of the domain, every x, every input, has exactly one output, right? It's a function if, when you know what the value of x is, you can figure out the value of y. Well, hey, this doesn't look like a function. It says a sequence is a function, so what qualification are we going to put on this? Something at least. A sequence is a function whose domain is the natural numbers. Huh. That's actually all you need to say. A sequence is a function whose domain is the natural numbers. And the natural numbers just means the counting numbers, 1, 2, 3, 4, 5, etc. Interesting. The sequence is just a function where the domain, the inputs, are restricted to the counting numbers. Okay, example. And we've got it right up here. This is squaring, right? It's perfect squares. So consider the function f of x equals x squared. You can probably even picture that. It's a basic parabola, vertex at the origin. Okay, but the natural domain for that is all real numbers. You can put in any value of x, not just the counting numbers. So let's change our notation a little bit. For sequences, we tend not to use FGH, but we tend to use ABC close to the beginning of the alphabet. And for the variable, for the input or independent variable, we tend to use N or M. And you might be familiar enough with that convention to even say, when I see N, it kind of feels like it's a whole number, not a fraction. So this would define a function. If we actually specify that N was just natural numbers, and you made an input-output chart for this, it would just look like 1, 2, 3, 4 for inputs, and 1, 4, 9, 16. You can start to see how this could be seen as just listing the outputs of a function. Like, this is the range, and we understand the domain is the natural numbers. Also, in addition, instead of writing a of n in standard function notation, we tend to shift our notation just a little bit and write a sequence, instead of with the of x or of n notation, a sub n, making the n a subscript. And then we think of this as defining the nth term. Well, the nth term is n squared, so the third term is 3 squared, the ninth term is 9 squared. There's your sequence, okay? Okay, let's see. I want to get into some of the calculator issues involved in sequences and summation notation. Let's see, my cameraman is kind of lax. So let's look at this example that feels more like homework or like the activity. Consider the sequence a sub n equals n factorial. This n with an exclamation point here is n factorial. I don't know, I'm probably standing off camera, huh? Here, is that somewhat better? The exclamation point is read n factorial, and here's a definition. N exclamation point, or n factorial, means n times n minus 1 times n minus 2. So it's defined for any natural number, any actually whole number, Like if n was 5, 5 factorial would be 5 times 4 times 3 times 2 times 1. You just take the number and multiply it by every other successively smaller number down to 1. And by definition, 0 factorial is also meaningful, and that's equal to 1. So let's write the first 4 terms of this sequence. And sometimes you see it written like this with this subscript notation, or it looks almost like function notation if you think a of n equals n factorial. But also you see in my math lab and the textbook this approach where you see set notation, like the squiggly brackets, right? And then just write the formula in here, and you understand that that means the sequence that you get when you put in 1, 2, 3, 4, 5. So the first 4 terms would be 1 factorial equals 1, and 2 factorial equals 2 times 1 equals 2, and 3 factorial equals 3 times 2, 1 factorial, 2 factorial, 3 factorial is 6, right? Because it's 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. So it's 24, right? 4 times 6. Yeah, 4 times 3 times 2. Interestingly enough, these terms get big really fast. And if you do 30 factorial, it's a pain in the neck because you have to multiply 30 times 29 times 28 times 20, 27, etc. And it's surprising how big these numbers get. So let me do this by calculator. And I'm going to shine the camera over here at the projector screen in my calculator. And let's find the factorial key on the machine. Actually, it's under the math menu. So there's a key here that says math. And for 30 factorial, I'll first type 30 on the screen. And then I'll press math. And I have to use a right arrow to go over here to the math probability submenu. And number 4 there, see the exclamation point, is factorial. So I'll hit the 4 key. And I have 30 factorial in my screen, and I'll hit enter. Whoa! I get a lot of stuff in here. This is actually a rather huge number, because this is calculator E's for scientific notation. This E means times 10 to the 32nd power. My goodness. So the 30th term of this sequence, I can come back to this board, the 30th term is actually approximately 2.65 times 10 to the 32nd power. And if I wrote that out in standard notation, I'd have to move the decimal point 32 times. So it would be a 2 and a 6 and a 5. And I need to move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a big number, huh? I won't bother putting in the commas. But 30 factorial is a humongous number. And if you experiment with your calculator, you'll find you don't have to go much beyond that to get to the point where you choke the calculator, because it'll only do scientific notation up to times 10 to the 99th power. Anyway, factorials are humongous. Okay, let's move on in some other stuff that you need for the activity in factorial. Yeah, sigma notation. Okay, so I should slap my cameraman here. There, slap. That will do. Okay, sigma notation. Like example, let's make it worse than that. Let's make it k over k plus 1. Okay, so this is a way of writing down sums, because we not only want to find terms of sequences, we want to find the sum of the first 4 terms, or the sum of the first 30 terms in maybe some extreme case. So this big Greek sigma, capital sigma, is short for sum or add up. When you see this, it means add up a bunch of things. This tells you where to start, k equal 1. This tells you where to end k equals 6. So there are going to be 6 terms here. We're going to do it for k equal 1, 2, 3, 4, 5, and 6. We'll stop there and add them all up. So what this means is let k equal 1 and figure out this formula. 1 over 1 plus 1 is 1 over 2. And then add what you get when k goes up one level. So it started at 1 and now it goes to 2. And you get 2 over 2 plus 1, 2/3. And then let k go up to 3 and you get 3 over 4. And keep following this pattern until k is 6, till you get to the end point, and then stop. And you get 1/2, 1, 2, 3, 4, 5, 6 terms, 1/2, 2/3, 3/4, 4/5, 5, 6, 6/7, add them all together. That's kind of troublesome to do by hand. You could do it, but the common denominator is going to be a pretty huge number, right? So let me do this by calculator. And of course, I could also do it by calculator by just crunching these. But I want to show you how to do it if you have maybe even 100 terms to add up or something ridiculous like that that you don't want to enter. So let me come back to the calculator screen over here. Okay, and I'll clear this out, and I'm going to go to a kind of a weird menu here. It's the list menu. It's the second function of the stat key here. There's a little blue word list that's hard to read. So I'm going to hit second and the stat key, and I'm going to get a list menu. And then I'm going to use my right arrow to go over to the sub-menu, the List Ops menu. Can you see that? Okay. And then under List Ops, I see Seq, S-E-Q, a sequence function down here at number 5. So I can press 5, or I can just enter Seq, sequence. And then the syntax here is a little bit sneaky. I have to put in the formula for the sequence. So in my example, I had k divided by k plus 1. Now, I'm just using my variable key. You could also put in some other letter, some other alpha character in the calculator if you wanted, but this is the easy way for me to put in k over k plus 1, just use the X button. And then I put a comma in here, and this is a little bit weird. The calculator just wants you to specify what the variable was that you used, which letter is the variable, X. And then put in another comma, and it wants to know where you start. We're going to start with x equal 1 or k equal 1 in the sigma notation. And another comma, and where you end, at 6, right? And close this, and this will just generate terms of a sequence. The first term of this sequence was 1/2, remember, otherwise known as 0.5. The next term was 2/3, otherwise known as 0.6666, and you know the calculator is round as far as it can. And I could arrow over here to get see the 3/4, and the 4/5 is 0.8, and the 5/6 is 8.3333. Okay. More interestingly though, if I want to add these up, I'm going to go back to my list menu, second list, and I'm going to go not to ops, but all the way over to math, and then the fifth option is sum. So I'm hitting 5 to get the sum up. Then I go back to the list ops menu and enter 5 again for sequence, sum of a sequence. Okay, so I'll hit number 5. See in my screen how I've got sum of sequence, and now I want to put all this stuff in here. So I'll say, here's my formula. Note my use of parentheses here, comma, x is the variable, comma, 1 is where I'm starting, comma, 6 is where I'm ending. And then I close parentheses for the sequence, but also close parentheses for the sum operator. So this is going to generate that sequence, but add them all together. And basically, the sum of all of this stuff, you can't see it as I'm writing on the board, is approximately 4.407. Okay, so this will be something you need to get used to using in the homework, the list ops menu, in order to find the sequence operator and the sum operator to add up the first terms of a sequence. The other thing pretty tricky that you'll have to do a couple of places is to just use this sigma notation. And I think probably the hardest thing that people ever do with this in this homework is to use sigma notation, is to write sigma notation, not only interpret it, but write it. So, for instance, if I had something like 1 plus 4 plus 9 plus 16, so I'm going back to my first example of squares, and then they said, write this sum using sigma notation. You have to be able to say, okay, it would have a big Greek sigma for add up. And then I have to find a formula that works for all of these guys, and just write it with a k instead of an n. So if you say, oh, these are perfect squares, so it's just going to come from k squared as a formula to generate each of these terms, and then say, where do you start? You can almost always work it so you start at 1. And where do you end? Well, I've got to add 1 squared plus 2 squared plus 3 squared plus 4 squared. I go up to 4 and then I quit. So this is just a sigma notation way of writing the sum of the first 4 perfect squares. Okay, last thing I want to do, and let's go back to the screen here. Okay, is I want to look with some apology at the, is this the, about the third page of the activity, of the second week assignment. These boxes here are places where the graphics didn't work. I had some formulas that just didn't carry through when I put them up on the web page. So I'm going to email attach an updated version of this that has those things filled in on it, okay? And hopefully by the time you're watching this, you've already received that. And then you can either just substitute this for that page, the better one for this page, or you can go through, if your writing is good, and spot that and say, oh no, that was supposed to be sigma from k equals 1 up to 4 of k squared plus 1. This, by the way, is a lot like the example that we just did, except instead of adding up the perfect squares, you're going to add perfect squares plus 1. So the first term in here will be let k equal 1. 1 squared plus 1 equals 1 plus 1 is 2. There's the first value in there. And that'll just be interpreting and using that sigma notation. I guess that's good, okay?